Good afternoon, everyone, and welcome to today's American School and University webinar entitled VRF Technology, the Ideal Heating and Cooling Solution for Student Housing, sponsored by Mitsubishi Electric Trane, U.S. HVAC. I'm Rob McManamy, Editor-in-Chief at American School and University's sister publication, HVAC Engineering, both of which are published by Endeavor Business Media. To begin with today, let me explain how you can participate in our presentation. First, if you have any technical difficulties during today's session, please submit to the questions window, and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on American School and University's website, asumag.com, within the next 24 hours. You'll be notified by email when the archive is available. Now I'd like to introduce you to today's speakers for our presentation. John Brooks currently serves on the education vertical team for Mitsubishi Electric Trane HVAC US, or METUS, working with K-12 schools and higher ed institutions across the Midwest, Northeast, and Mid-Atlantic regions. John helps bring innovative and energy-efficient variable refrigerant flow technology into educational facilities. He holds a bachelor's degree from the University of Iowa and has over 9 years' experience in the HVAC industry. Jay Wesson has spent the majority of his career overseeing facility maintenance, along with planning and managing construction projects for schools and hospitals of all sizes. In his current role as the senior construction manager at Texas State Technical College, he directs both new construction and retrofit projects, working with vendors to optimize scheduling and resources. Most recently, he served as the director of facilities and construction for San Marcos Consolidated Independent School District. He holds a bachelor's degree from Abilene Christian University. Well, we'll start with John Brooks. So, John, welcome, and please go ahead, sir.
Well, thank you, and good morning and afternoon to everyone in the audience. On behalf of the nearly 500 Mitsubishi Electric HVAC US employees, I'm happy to say thank you for sharing some of your time with us today. In this webinar, we will define the common terms of VRF technology, discuss how VRF heating and cooling is very cost-effective in student housing applications, and hear about a recent project at Texas State Technical College. To bring everyone onto the same page, let's review the basics of variable refrigerant flow technology, along with its operation and how it can be applied. VRF systems consist of an outdoor unit. Some folks call this the compressor or condensing unit. This is then connected to a network of indoor units, which can also be called fan coil units. Many different styles of indoor fan coil units are available to suit your application and design goals, some ducted and others ductless. VRF systems heat and cool the zones of your building by moving refrigerant through small diameter piping. That's the main idea here. We move the refrigerant rather than cooling and then moving air or water. During colder months, these systems draw heat from the outside air and bring that heat via refrigerant to zones calling for heating. And during hotter months, the system pulls heat from your zones via the indoor units and exhausts that heat to the outside air. In contrast to VRF operation, a conventional HVAC system typically takes a centralized approach, where ductwork is connected to a centrally located air handler. You are all likely familiar with some of the long-standing issues with these systems. The more ductwork you have, the more potential for air leakage, requiring balancing and service. When there is a drop in performance, the extra ductwork can make it difficult for contractors to pinpoint the problem. And as we'll see in the next slide, the conventional method of on or off operation results in the entire system turning off when a set point is reached, then slamming back on when the set point slips. This is very inefficient. Other conventional systems, such as PTACs, are certainly set up differently, but can have their own cost-related issues. Not to mention, they aren't aesthetically pleasing and can be noisy, which is not a pleasant housing experience. Here we can see a comparison of conventional HVAC operation to VRF. VRF systems use inverter-driven compressors, shown in the green line, which modulate energy usage instead of constantly slamming to 100% and then stopping like a conventional system. A great example is driving your car. If you drive like a conventional HVAC system, you would floor the gas pedal anytime you dropped 5 miles per hour below the speed limit, then completely coast until you needed to floor it again. You can imagine the resulting fuel economy or energy efficiency, and you may have seen one of these folks driving into work today. Looking now to the green line, consider the cruise control in your car, gently modulating the throttle up and down as needed to just maintain the set speed. Operating this way allows the system to keep up with the high energy demands of a student housing facility while also maintaining energy efficient use. Let's also consider the comfort this inverter-driven compressor gives us. Instead of the room constantly moving into and out of set point, we have a consistent supply of set point comfort. VRF technology also allows for indoor air temperature to be customized by zone. The example shown here depicts a building with simultaneous cooling and heating. Imagine the area with the blue arrows to be in cooling mode, while the area in red is in heating mode. This is what we call a heat recovery or simultaneous VRF system. Because the same outdoor condensing unit can supply cooling to some zones while recovering some of that heat, adding to it, and sending that same heat to other zones in the building. And we'll talk more about heat pump systems versus heat recovery systems in the next few slides. On a less drastic scale, VRF zoning allows set points to be a couple of degrees higher or lower, even if the entire building is operating in one mode. Again, think of the comfort this allows. Occupants can have set points several degrees apart without needing the system to change modes. In a crowded space, for instance, occupants may appreciate the air to be slightly cooler than in a more open area. Think of our student housing application, which may have a kitchen, a gym, student suites, and common areas. A VRF system is a great choice for managing all those different set points. Here we see a heat pump only system. All the indoor units are either red for heating or blue for cooling. In single zone applications and in moderate climates, heat pump systems are a very cost-effective option when each of a building's zones can be in the same mode at the same time, either cooling or heating. Also consider larger common spaces such as a lunchroom or auditorium where the whole space is set to a common set point. Here we see the heat recovery system, with some indoor units in red for heating, while others are in blue for cooling at the same time. These systems send heating and cooling to multiple zones in a building by cycling the refrigerant between the outdoor unit and the indoor units via the branch circuit controller in between them. Note how the branch circuit controller is the only difference between a heat pump system and a heat recovery system. You can think of the branch circuit controller as the traffic cop, sending cooled refrigerant to some zones and heated refrigerant to others. Student housing applications generally require simultaneous heating and cooling, or a heat recovery VRF system, because there's a lot of activity going on in the building. Student rooms may need to stay warmer while common areas cooler. Likewise, zones without occupancy can idle, while full rooms and kitchens receive 100% capacity. We've just described how VRF systems can operate as heat pump or heat recovery. There are also two different mechanical options, air source and water source. Both options provide optimal energy efficiency and comfort. They differ only where they capture or reject heat. Choosing between them comes down to location, efficiency goals, and existing equipment of your building. Looking to the image, this is nearly to scale. The taller unit on the right is an air source outdoor condensing unit. The blue areas are the coil, and the round stacks house the fan, which pulls air through the coil to either reject or capture heat. The shorter unit to the left is the water source condensing unit, which is nearly the same machine but without the coil or fan. Note the circular punch-outs near the bottom. These allow connection to a water loop, so the unit can capture or reject heat to the water. Water source systems rely on chilled or heated water to regulate the refrigerant temperature year-round. Water source condensing units may be served by any water loop you like: independent cooling tower or flat cooler, a campus water loop supply, a geothermal field, etc. Another helpful feature of VRF systems is the variety of indoor fan coil unit options. VRF indoor units are very compact, saving space and offering many aesthetic and application-specific choices. The total building system can be made up of as many different styles as needed, allowing excellent flexibility of design. Looking to the image, if you consider the ceiling tiles of that foyer could be connected to ducted units, while other rooms could be served by the traditional wall-mounted unit at the lower right. And the black vertical unit is sized and shaped to take the place of any existing residential-style vertical air handler. Contrary to outdated ideas based on long discontinued equipment, today's VRF heat pumps are able to provide heating in extreme cold. With hyperheating technology, you can ensure students and staff are comfortable year-round with or without auxiliary heating. And in climates where design temperature requires backup or auxiliary heat, the extended low-temperature performance of today's heat pumps allows complete shoulder season heating via the VRF system, greatly reducing the load and operating time of that auxiliary heat system. Let's shift gears a bit and talk about ventilation. Indoor units of a VRF system are only heating or cooling the air already inside their zone. There is a benefit here to improved indoor air quality because a cough in room 1 is never transferred to another room by the HVAC system. Both energy recovery ventilators, ERV, and dedicated outdoor air systems, DOAS, are commonly used to provide fresh ventilation air to buildings using VRF cooling and heating. ERVs recover waste energy from a building by capturing and repurposing the thermal energy from the exhaust air. They move the exhaust air through a heat exchanger where it tempers the incoming air as the exhaust is leaving the building. Through this crossing of the streams at the heat exchanger, the ERV recovers about 70% of sensible energy and 60% of latent energy. ERVs are most cost-effective in moderate dry climates. In more humid climates, a DOAS, a dedicated outdoor air system, may be a better solution. A DOAS can condition up to 100% of the ventilation air load. In this way, the DOAS can provide a lot of humidity control to the building as well. In colder climates, a DOAS may also be sized to assist with the heating demands of the building. Depending again on sizing requirements for the building, the heating and cooling of the DOAS system may be provided by a VRF condensing unit, keeping another component of the facility off fossil fuels. At this point, we've described how VRF systems provide very precise energy usage due to the inverter compressors using only the exact amount of energy needed to reach a zone set point. What if that building also wants to track individual energy consumption or be able to bill tenants per their specific energy use? In these applications, energy allocation controls can be applied to the VRF system. This solves the challenge of energy consumption billing for multiple tenants. The energy allocation software is added to a VRF system's controls and an energy meter is added to track the consumption of the condensing unit. This feature is ideal for off-campus student housing communities. For buildings where the projected energy usage and utility bills are built into monthly rent. The energy efficiency of VRF systems creates opportunities to offer more competitive leases. So what types of projects can benefit from a VRF system? Small, large, new construction, retrofits and historical renovations? I need an option E for all of the above. For additional context, the top picture on this slide is the Hollis Primary School in Hollis, New Hampshire. This K-12 school was built in the 50s and was in desperate need of an energy retrofit. Utility expenses were through the roof and the school was uncomfortable in every season. The school board selected VRF for efficiency, operational cost savings, and their commitment to sustainable practices. And the second image is Fairmont State University, a small public university in West Virginia. This was a new construction project. They added a 3-story student housing building to accommodate 345 students. While a VAV system was originally planned for this application, VRF proved to have a much better payback cycle. Okay, now that we have some baseline knowledge on VRF technology, let's dive into today's example, Texas State Technical College. Jay is going to start by sharing some of the stats on the school and what requirements they were looking for in an HVAC system. Take it away, Jay.
Okay, thank you, John, and thank you all for attending today. I'll start by giving you a little bit of background on Texas State Technical College. The college was founded in 1965 as a technical institute, and TSTC was created to meet the state's evolving workforce needs. Our curriculum today is designed to reflect real-world working environments. We have a diverse range of programs from culinary to welding. Our goal is for our students to be employable and job-ready at graduation. We have 10 campuses across the state of Texas, but the project that we'll be discussing today is on the Waco, Texas campus. The Waco campus was really an Air Force base, and there is still an operational airport on the campus. Along with the airport, there was also base housing on campus. This housing was used to some extent for student accommodation, but with age and much of it becoming expensive to maintain. Therefore, it was decided to build a residence hall for some student housing, and this project would allow us to also establish some green space by demolishing much of the old air base housing. With that said, the Facilities Planning and Construction Department was given a budget of $22 million to develop a new residence hall to house approximately 244 students. The hall has both single and double occupancy units, and the building is just under 100,000 square feet. Obviously, there are a lot of factors that go into planning a building like this, but the HVAC system selection was a pretty critical piece for us to decide on. As you see on the screen here, we wanted a single system for simultaneous heating and cooling. We needed it to be energy efficient, we needed it to be cost effective, while also offering installation design flexibility. The construction method on this project was design build. And as we went through the design, the A&E team initially specified chilled water. However, as cost estimates came in, there was a little bit of sticker shock. The estimated cost for piping, wiring, equipment, and installation was about 30% over what we had allocated for conditioning the building. With some previous experience with VRF, I thought we should look at some options, not only from a cost perspective, but also from a simplified design and operation and maintenance perspective. As you all know, us old maintenance folks don't want anyone to move our cheese or change things up, so there was a little bit of apprehension at first, but once the team understood the potential for cost savings and the benefit of VRF, it was a no-brainer for this project. We have a centralized controller for this building, which allows our maintenance staff to manage all of the indoor and outdoor units from a single interface. This lets our facility staff troubleshoot and resolve many issues before having to disturb students. We have a heat recovery system, provides simultaneous heating and cooling, which is ideal for our building needs. On the timeline, which was during COVID, we broke ground on the project in August of 2020 and were able to open our doors to tenants in August of 2021. In terms of our decision to go VRF, there are several benefits that come to mind. First, the design flexibility of the system. For this building, we went with mainly ducted indoor units. However, we do have a few ductless. We went mainly with ducted indoor units, but we have a few ductless units as well. We predominantly use the ceiling concealed units. They are super flexible for install and have a low profile look. The compact design of the system was also helpful to the engineer and the architect as they planned the layout of the building. Of course, the compact design also gives added room to some spaces. Another benefit is streamlined operation. We've already touched on the controls a bit, but zoning is a key benefit of VRF systems. And with the controls interface, the system responds quickly to inputs or schedules. As mentioned earlier, remote management also always helps us to run our system as efficiently as possible, whether maintenance staff are on or off the campus. We did choose the Mitsubishi DOAS for controls. However, as we went through this, I was pleasantly surprised to learn that the DOAS will integrate with other manufacturers' equipment when or if it's necessary. Our student rooms do also have individual thermostats. In other words, we do allow the students to have some control over their environment within reason. Third, maintenance. VRF systems are more cost-effective and simpler to maintain than traditional systems. One reason that is true is because VRF allows multiple indoor units to join with a single outdoor unit. A typical maintenance routine includes monthly coil washing, drain line maintenance, and quarterly air filter changes. And like I mentioned previously, it took a little time for our maintenance staff to understand VRF, but the sheer reduction in units compared to something like chill water makes preventive maintenance of the system less cumbersome. Lastly, when you're housing students year-round, it's critical for maintenance and facility staff to understand how to use the systems properly. So facility staff training and support is critical. METUS has supported our facility staff with initial support and training. From there, they have done several in-depth trainings with us, and it's nice to know that they are only a phone call away for any technical support. They have truly become an extension of our team. Last but certainly not least, and it's not on the slide, but VRF brought our project for conditioning the building back into budget. With that, do you have anything else to add, John?
Well, sure, Jay. Great work. At METUS, we have the whole country split into a series of business units. Each business unit has a commercial team and a residential team with area managers in most major cities, along with mechanical engineers, office support, and service teams. Each business unit is also supported by a member of our education vertical market team. That's the team I work on. The education team works in an end-user direct model, so we communicate directly with folks like yourself at school districts and higher ed institutions, while our colleagues on the commercial business teams call on the architects and mechanical engineers. By splitting the project into the team working with the engineers and the education team working directly with the school, METUS is able to support a project all the way through, from introducing the technology and its benefits at a school board or capital project team meeting, to making sure the design engineers have all the relevant equipment information, and finally, providing installation support and owner training as a project gets built. Also, as you educators and facility staff attend your conferences and trade shows, it will most likely be the education team you meet at the METUS booth on the Expo floor. And finally, I want to promote our learning management system. This is a series of over 100 hours of free online video training developed specifically for school facility staff. It consists of 3 tracks, one for project management, one for installation, and one for service and maintenance. Before we get into the Q&A, I'd like to show this comparison. Jay mentioned first costs, particularly equipment and installation were a major factor in his team choosing VRF technology. I can provide some further detail on a similar scenario. Our education team worked with a third-party engineer and contractor to develop the comparison you see here. We wanted to show a very common student housing application for new construction. This is HVAC based on individual, conventional, centralized systems that split the air conditioner and heating equipment. These solutions get installed all the time, but not only are these super inefficient, they are a cost and design nightmare if you really consider a holistic view. Considering the piping number, each of the 236 conventional units requires a home run of refrigerant piping from the apartment to the roof. That is a lot of piping. And think of the vertical chases through the building required to fit all that piping and insulation. Now, by comparison, on the VRF side, only the 14 outdoor units require home runs, as it is the branch circuit controllers which use a home run, not each individual apartment. And looking to the electrical cost, this project was modeled against these seemingly inexpensive split units with roof-mounted condensers for AC and electric heat for heating. Well, those electric heaters require 15 kW of electricity, and depending on line length, that 15 kW is going to require 40 or 60 amp breakers, along with number 4 or number 6 wire size. Again, that's a lot of copper. Now, compare that to the VRF side, and there is no electric heat needed. Only a single 15 amp breaker, and again, depending on line length, number 10 or number 12 wire size. So looking to these details together, even with the higher price of the VRF equipment, it's still a better decision to go with VRF. As a few takeaways, consider how the inverter compressor allows VRF to consume only the precise energy required for each zone. Consider that VRF offers a variety of indoor unit styles to match design and function of your next project. And consider that VRF offers a simplified operation and maintenance, along with energy efficiency and cost savings throughout the life of your building. At that point, I'll hand it over for some Q&A.
All right. Thank you. Thank you, John. Thank you, Jay.
Oh, I'm sorry, Andy. This is Rob. I'm sorry, I was on mute there for a moment, but no, thank you, John. Thank you, Jay. I was going to hand it over to Andy Salage here to handle the Q&A. My apologies there. But Andy, over to you.
All right. Okay. All right. Thank you for the excellent and educational presentation, John and Jay. We have questions that reflect varying levels of familiarity with VRF, and if we don't get to your question, one of our subject matter experts will reach out to you after the fact. But thank you for submitting, and John and Jay, let's get right into it. All right, first question. Can you describe the difference between a heat pump system and a heat recovery system?
Sure. This is John. I can speak to that. Both systems are going to require a condensing unit. So whether that's the outdoor air source or if you have a water source system, you're always going to have that condensing unit. That's what's creating the heating or the cooling. And likewise, you're always going to have a series of indoor fan coil units throughout your building, one in each zone. the difference between heat pump and heat recovery is one piece of equipment, whether it has a branch circuit controller in between the outdoor and the indoor. If it does not have that branch circuit controller, it would just have a series of header pipes and T-pipes to direct the refrigerant directly from the outdoor unit to the indoor unit. And again, the function of that branch circuit controller is to provide the heat recovery action. So the branch circuit controller as a piece of a heat recovery or simultaneous VRF system, that's the piece of equipment that allows you to be cooling in one zone and heating in another zone at the same time. A heat pump system, all zones must be in heating or all zones must be in cooling.
Okay, great. Jay, if you don't have anything you want to add to that, we'll move on to the next question.
I'm good. Thank you.
All right. Okay, next question. Earlier, we mentioned that VRF works in cold climates. So how does hyperheating work?
Sure. So hyperheating is our brand name for our most capable type of condensing unit. If you compare the condensing units to pickup trucks, for example, you've got an F-150, an F-250, and an F-350, again, increasing capacity there. Our condensing units are organized in a similar fashion. We have what's called standard efficiency, and then high efficiency, and then hyperheat. Hyperheat runs to the lowest outdoor air temperature while still producing heat for your indoor zones. And the way that works is there are two operations kind of feeding each other. The compressor is able to run at a higher than normal speed, providing extra heat from the refrigerant cycle. And at the same time, the equipment allows a stream of refrigerant to kind of flow through the top portion of the compressor housing, which pulls some of that excess mechanical heat, again, generated by the compressor overdriving. It pulls that excess mechanical heat out, again, to be contributed to the refrigerant cycle. So it's those two actions kind of happening at the same time.
Perfect. All right. This next person, and Jay, you may want to jump in on this one. This person is working at a university that has some pretty stringent sustainability and efficiency protocols and measures, but they still want to give the students some control over their environment. So with VRF, how are the controls set up so that we can monitor the temperatures in the student suites as well as the energy use?
Well, John, you want me to go first on this one? We set it up where we give them probably a 4-degree temperature range from 68 to 72, depending on the time of year and the temperature outside, for them to control, for the students' control. We do monitor the energy in the building, but we don't monitor it by room. The energy use by room. We do, of course, try to have some energy efficiency in every way that we can, but through things that won't affect the students as much. We, of course, have some lighting controls as well for energy efficiency, but we don't. We just give them a narrow range of temperature to go to. That's how we manage what the students use. I don't know if that answers the question, but I believe the control system, and John can answer this better than me, they can do a lot more gauging and get more reports from them than we are using at this time and on our system.
Sure, Jay, I can add one more flavor to that. So again, there's kind of two functions that can happen at the same time. Previous HVAC systems, more conventional HVAC systems, it was very difficult to offer different zones of the same building a truly independent set point. Because of how VRF functions, with each indoor unit only requiring the refrigerant that it is calling for, you really are able to offer your occupants independent set points, and those set points are not going to greatly impact the resulting energy cost. So that's kind of the first idea. Is it just previously you weren't able to do that, now you can. To answer the second part of the question, if an organization wanted to really sub-meter or offer a billable total, that's what we call the energy allocation. And there are two components to that. There's a hardware component and a software component. The hardware component would be a electrical consumption meter that is added just directly in front of the condensing unit. You just want to know the energy of that condensing unit. The software side gets added, and the software looks at how much refrigerant the condensing unit is sending to any given zone. It knows the amount of refrigerant, and because of the utility meter, it knows the amount of electricity. So it can create a billable consumption for each zone by comparing those two numbers.
All right, excellent. So here's a question regarding redundancy. So can multiple condensers or outdoor units be put together to provide redundancy? So the idea would be, if there's a problem with one unit, perhaps the other can pick up the load and keep the residents comfortable. Is that possible with VRF?
Sure, I can speak to that.
Sure.
Is it possible? Sure. I don't know that it would necessarily be needed. There are some hard limits. For example, if you had one condensing unit, there is a maximum of 50 indoor zones that could be connected to that one condensing unit. Now, we don't recommend that. Typically, there's a real efficiency sweet spot for VRF systems in kind of the 8 to 10 ton zone. And again, that's my sales guy speak, so forgive me if I'm a little off on my tonnage. But what we typically recommend are, perhaps more than one smaller system. And when you think system, just consider how many indoor units connected to one condensing unit. That would be one system. So you might have two systems, maybe three systems feeding a building. And that, again, is an energy efficiency sweet spot. And in a worst case scenario, if something were to fail, then a smaller number of zones are affected.
Jay, do you want to comment, or do you, because I have one that's right?
No, I mean, I'm kind of like John. I don't know that would be very cost effective to try to have them hooked to more than one. But I'm not near the technical expert that John is, so I'll leave it at that.
Okay, well, we have one that's directly addressed to you, so
okay.
And it's a two-part question. So, do you believe that you're going to use VRF for any future projects? And do you see, are you doing any trending to see if this building, the building we did the case study on, is more efficient than other buildings on your campus?
Absolutely, I believe we'll use VRF more in the future. I used it as you mentioned in my bio. I used it at a previous school district that I worked in, and it was very efficient for us and also very good for the staff because, of course, we used it there in an office space where we might have 6 or 8 offices in the front of a school building, and everybody could control their own temperature. So that was very good public relations and good for the school district. And I believe we'll continue to do that here for office space. Of course, for a time during COVID, we actually had planned to build a huge building with a lot of office space, and we would have gone VRF with it probably as well. This project that we used was, as I mentioned earlier, was design build. So the architect in that method of construction, the architect actually works under the contractor, and that's why it was questioned here at first, or that's why we didn't determine to do that from the very beginning. But it certainly was good for us, and we will definitely be studying that building and size and seeing how it does efficient-wise compared to other buildings. Does that answer the question?
I think it does. So, John, if you don't mind, I'd like to move on to this next one. It's a general question, but that's not related to the technology itself. Are there tax credits available for VRF, either specifically for VRF or perhaps for heat pumps in general?
Yes, that is a very good question. And the easy answer is yes. There are certainly tax credits available. And there have kind of always been rebate monies available, and there was a lot of T's to cross and I's to dot to make sure that you got the money back. With some of these tax programs, and specifically into the next several years with the what's called the Inflation Reduction Act, there's going to be a lot more monies available for adding electric cooling and heating, or perhaps taking a building off of a fossil fuel. So again, still several ins and outs. And again, my sales guys speak here. I don't have all the detail for you, but when we finish out this webinar, our contact information is going to be available to everyone. And again, the Mitsubishi Electric team that is spread across the country, we've got folks in every state. We have staffing available to help you find the answers to those questions. There's a whole team of folks, similar to like the education vertical market team that I work on. There is another team that's called, I believe it's strategic buildings and utility incentives, or something similar to that. But there's a team of 5 or 6 folks, again, covering different areas of the country. And it's their job to know what rebate money, tax incentives, what monies are available to help projects. So again, please do consider us at your resource. We can help you find those answers.
Excellent. All right, so we have several questions regarding controls. So I'm going to get to as many of them as we can. First one, how critical is it for the VRF system to include a central controller configured for the system as opposed to using an existing standard BAS?
How critical is it to utilize a central controller?
Yes. And one configured for the system as opposed to
sure.
Standard.
There's kind of a fundamental difference in any brand of VRF equipment versus something like a chilled water system or a series of rooftop units or a VAV system. All of those other systems, conventional systems of really any flavor, are made up of individual pieces of equipment that are then collectively told what to do by a separate controls system, right? So whether that's something from Johnson Controls or Honeywell or Schneider Electric or Siemens, any of the big controls names, they are geared towards these individual pieces of equipment that all need to be coordinated. Now, if you compare that to a VRF system, you really have to just start at zero and think, okay, this HVAC system is based off of, in some cases, one condensing unit. The real brains of operation reside in that condensing unit. And then in addition to the piping that makes up the full system, there's also a little bit of control wire that makes up the system. So the real baseline operation controls are completely built in to the equipment, and they can be set up at a building commissioning. And if you never wanted to touch it again, you wouldn't have to. The system can just run itself. It'll modulate up and down, meeting the set points it has been told to meet. The kind of criticalness of adding a central controller, it's just kind of based on size. If you've got a lot of indoor units, you've got 1 or 2 or 3 building operators that need to have access to it, maybe view an alert, clarify a set point, change a schedule for one specific room. That's really where the central controller becomes very useful. You can walk up and make changes by pushing the touch screen on the wall. or you can make changes through a terminal computer front end. So it's a little bit dependent on the building, but that criticality of it, I think, is more the question of separating a VRF system from other conventional HVAC, where quite a lot of the controls are already built into that condensing unit.
Excellent. Now, just short addendum to that, because it's a question a few people ask. Can VRF be integrated with a VAS?
Yes, absolutely. Any size and scale of a VRF system can be integrated to any of those control brands I mentioned, and there are two things I'll point out about that. Number one, again, for any brand of VRF, when you are integrating it to any brand of controls, let's just pretend that an indoor unit in Office 101, let's pretend that indoor unit has 90 different control points, 90 different data points. Any controls integration to a BAS, a BACnet system, the integrator is going to need to choose from those 90 points and write a custom integration for however many are ended up to be chosen. If they say, okay, we really need these 30, then those 30 need to have an integration written for them. Now, by quick contrast, one of the benefits of Mitsubishi Electric Trane has their own controls division, and that controls division was given the full driver for Mitsubishi Electric equipment. So if you have that building, you want to put a VRF system into it, you want to have complete visibility in a very plug-and-play fashion, Mitsubishi Electric Trane is the only brand of VRF that can provide that full functionality through Trane controls.
All right. Excellent. Okay, so we're going to move off of controls for a second. So can VRF systems be used in spaces that are not occupied by residents? So maybe, let's say, a private school that doesn't have housing, like a K to or a K to 12.
Oh yes, certainly. VRF in general is a great system if you think about it in a renovation sense. If you have a private or a public school, but perhaps it's an older building, maybe some older unit ventilators, or simply a system of some kind of radiant heat, whether it be hot water or steam-based. If you consider bringing a new HVAC system into that building, when you distribute the indoor units for a VRF system, you only need to punch very small holes through the walls to bring that copper tubing to each indoor unit. So you're not breaking big holes to bring in new ductwork. You're not punching a whole bunch of holes in the roof for individual rooftop units. So it can be a very cost-effective way to do the install because it's less invasive.
Okay, perfect. This is a question about integration. So can VRF systems tie into existing hot water, high efficiency water heaters, like in a gymnasium, for example, but add cooling?
Yes, absolutely. In either a gymnasium, an auditorium example, or even that older school example that I just gave, consider if you have a kind of mechanically healthy heating system of whatever flavor. If that system is doing a good job, if it's been recently invested and maintained, you could look at adding cooling via a VRF system. Now, there's a benefit there. If you have a project in mind to add cooling, consider that bringing a heat pump to the building, not only do you add cooling, which is your primary goal, you're also adding what I like to call shoulder season heating. So I live in Minnesota. I serve a lot of territories that have significant winter months. And let's say that at one of these older buildings, you might turn a boiler system on in, sometime maybe mid to late October, and you run that boiler system until sometime, early to mid-April, March, whatever your season dictates. If you bring a heat pump to that same building, not only do you get the air conditioning because that's the primary purpose, but you take that heat system, that boiler system, whatever it is, you can really trim down the usage of that system. So now maybe you only turn that existing heat system up in December, the coldest days of December, and you're able to shut it down again, perhaps into February. So not only are you adding air conditioning, you can really deem that to be a strategic electrification project because you're able to really trim down the fossil fuel consumption of that existing boiler. I've had state universities or some larger private colleges talk about how they'd like to trim the consumption of their central plant. Same idea goes in that example. You could take a building that has a bad condensate return level, or simply the building that's the furthest away with the most pumping losses. Bring a VRF system to that specific building, and it's a very strategic electrification of the campus.
Great. Jay, haven't forgotten about you at all. We have this next question I think both of you can chime in on. So with VRF systems, is it recommended to shut it down over a long break, like perhaps the upcoming holiday break at a public school?
Well, as for me, and John May can answer this better than I can, but for us at K-12 and on in our dorm, if they're gone for the Christmas break, we don't technically shut it down. We do check the thermostats in the room to make sure it's, not overheating or overcooling, or set their temperatures real low. But and the school district's the same way, but we left the system up and running. No training I ever had was ask us to shut them down. So, John,
Yes, sir. I would confirm and agree with Jay's statement there. A VRF system can certainly accommodate a setback schedule. A conventional system, if you put it into setback, if you've got a 70-degree comfort set point, and you let the in a heating example, maybe you let the building cool down to 65 or even 60 overnight, or perhaps on a period of break. A VRF system could do just exactly the same thing. When the set point comes back into recovery, when you go from that 60-degree back up to your 70-degree comfort, the VRF system, it will ramp up. It'll ramp up high into capacity to meet that set point, but then again, modulate down to just maintain it.
Great. Okay, I'm going to combine a few questions. So, there's one specific part. So, Jay, what was utilized to bring fresh air to TSTC? But more generally, how do you handle ventilation, outside air with VRF systems?
Bring fresh air into the building?
Yes. How do you bring in fresh air for the students and staff?
Just through fan coil units on the exterior, can bring in some excess air if we need to.
And I could offer that. How is it typically done?
Mm-hmm.
It's a little bit of a different design than what some folks might be expecting. They might be expecting, okay, brand new, up-to-date HVAC system. We're going to put one system in there and it's going to do everything we need. Well, a slight edit to that. With a VRF system, like I mentioned before, that individual indoor unit is cooling and heating the air already in that space. But you do need to meet ventilation requirements. So again, typically this comes out, and engineers across the country are very familiar with this scenario. So don't be discouraged if perhaps you've not seen it yourself. And again, certainly no offense there. I can assure you that folks out there in your architecture and engineering communities are very well versed in this. It would be a VRF system, again, for each zone, offering that comfort, heating, and cooling with that dedicated outdoor air system in some cases, which might be a large typical rooftop unit with, again, a small set of ducting into each classroom. If you consider a rectangular classroom, you might have a ceiling cassette in the center of the room, installed in the ceiling, and that would be your indoor unit. So you're bringing the hot air up from the room and sending it back out as cooled or heated. And in a corner of the room, just on its own little piece of ducting, there would be air coming in from the DOAS. And that DOAS might be set so that it's providing what we call tempered air or perhaps room neutral air. So you're not trying to do all of the heating and cooling requirement with that DOAS, but you're just bringing it to kind of a tempered state so that then the VRF system can provide the bulk of the heating and cooling.
Yeah, right. And I kind of misspoke there. Yeah, we use the DOAS, or that dedicated outdoor air system, is used as well on our system at Griffith.
Gotcha. All right. So this next question concerns the branch circuit controllers. We actually could combine some questions that are used with heat recovery systems. So one, what kind of maintenance is required for a branch circuit controller? And then how many indoor units can one branch circuit controller serve?
Okay. The maintenance is a good point. As you all know, there are a couple of brands out there offering VRF systems, a couple of brands, different branch circuit controller designs. The way Mitsubishi Electric and Trane provide the branch circuit controller, when it gets installed, you will most oftentimes want to have access to the bottom of the unit, right? So if you imagine that branch circuit controller up above you, you'd have an access panel in that portion of the ceiling so that if needed, you could get to it. The bottom sheet metal panel of that branch circuit controller can come off, and individual components within may be serviced if needed. The branch circuit controller from Mitsubishi Electric Trane, it does also have a condensate drain. Typically, there's not a whole lot of condensate that comes out of that branch circuit controller, but because we do accomplish the heat recovery action in the branch circuit controller, there can be a little condensate as things warm up and cool down. The sizing, again, you're catching the sales guy on his toes. I think we offer them in a few different sizes. I believe the largest is a 16 port. I think I'm right there. And actually, there's another benefit to that idea of how many ports can be on one box. If there are questions out there about future expandability of a VRF system, it really is best to go with heat recovery, which includes that branch circuit controller, because that branch circuit controller may then be specified with some extra ports. So if a wall needs to be added somewhere, one zone now becomes two zones, you have that extra port on your system. All you would need to do is add the piping, add the indoor unit, adjust the controls a little bit, and there you go, you've got your expansion.
All right, perfect. All right, this is our very last question. What is the typical life expectancy of a VRF system?
Great question. We pretty flatly say 25 to 30 years. A lot of that obviously comes down to installation quality, making sure that the system is purged with an inert gas when your copper tubing is being brazed together. We at Mitsubishi Electric Trane, we have a whole series of steps that are followed with the installing contractor to help ensure that any customer receives not only a 10-year parts warranty, but also a 10-year compressor warranty. This is what we call our extended warranty. And beyond that 10 years of warranty, we really do believe that if these units are installed and given the maintenance that they need correctly, you should get 20, 25, perhaps even 30 years out of it.
All right, thank you. That's all the questions we have time for.
Well, very good. One last slide here, just to throw up some additional resources. MitsubishiComfort.com. You can find case studies there as well. Find a contractor in your local area. And that, folks, is my email address there directly. Any questions you may have, please reach out. If you're in a different area of the country than myself, I may point you to a more local member of our team, but we are very happy to assist.
Well, thanks very much, John, and thanks, Andy, for the Q&A session there. Thank you, Jay, for your time with us today. I'm afraid we have run out of time, but that was a great presentation, and thanks again to all our presenters. And for those questions that we didn't have time to get to today, we'll be getting back to each and every one of you via email. As a reminder, this presentation will also be posted at asumag.com within 24 hours, so look for it there as well. So that does conclude today's presentation. On behalf of American School and University, I'd like to thank our speakers, as I just did for the presentation. I'd like to thank Mitsubishi Electric Trane US HVAC for sponsoring today's webinar, and of course, all of you for joining us. Have a great rest of the day and a wonderful, safe, and warm holiday season. Thanks, everybody. Bye-bye.